What is the critical point in substances, and why do phases vanish? Imagine a moment where the line between a liquid and a gas completely disappears, and they become one. That's what happens at the critical point in a substance. It's a special spot on the phase diagram where the properties of the liquid and vapor become identical. At this point, you can no longer tell them apart because the boundary or interface between the two phases just vanishes. Instead, the substance exists as a supercritical fluid, which has the ability to act like both a liquid and a gas. To understand this better, think about how normally substances change phases. For example, water freezes into ice or boils into steam at specific temperatures and pressures. These changes happen along lines on a phase diagram. The critical point is at the very end of the line that separates the liquid and vapor phases. Beyond this point, increasing pressure or temperature doesn't turn a gas into a liquid or vice versa because the physical properties of the two phases start to match. Their densities, for instance, become the same, meaning the molecules are packed in similar ways whether they are in a liquid or a gas state. Now, why do the phases vanish at the critical point? As the temperature and pressure approach their critical values, the density of the vapor increases while that of the liquid decreases. Eventually, they become equal. When this happens, the surface tension that normally exists between a liquid and a gas disappears. Without surface tension, there's no clear boundary, so the phases blend into one another seamlessly. This creates a supercritical fluid that can diffuse through solids like a gas but dissolve materials like a liquid. The critical temperature is the highest temperature at which a liquid can exist for a given substance. If you go above this temperature, no amount of pressure will turn the gas back into a liquid. The critical pressure is the minimum pressure needed to liquefy a gas at the critical temperature. These two parameters are different for each substance because they depend on how strongly the molecules attract each other. Substances with strong intermolecular forces have higher critical temperatures and pressures. Understanding the critical point is important in many industries. Supercritical fluids are used in processes like decaffeinating coffee or extracting essential oils because they combine the best features of gases and liquids. They are also key in designing equipment for refrigeration, power generation, and chemical manufacturing. Knowing where the phase boundary ends helps engineers control processes and avoid unwanted phase changes. In summary, the critical point marks the end of the line where liquid and vapor phases are distinguishable. Beyond this point, the phases merge into a supercritical fluid, which behaves differently from either pure liquid or gas. This unique state opens up many practical uses and helps us better understand how substances behave under different conditions.